Hello, and welcome back to our series on vertex operator algebras. In this, our 26th episode, we're beginning Chapter 2. This chapter is going to be all about the calculus of formal series and how it relates, or more appropriately, how it tries to represent quantum fields. Let's begin with a quick review of some key facts about affine Lie algebras we learned in Chapter 1. Suppose G is a Lie algebra. Recall that we can build the affine Lie algebra over G by taking the tensor product with the Laurent polynomials in some formal variable, say t, possibly with some central extension. As we studied extensively, it is useful, often, to append the derivation of those Laurent polynomials to this algebra. If we started with an abelian Lie algebra, one whose elements all commute, the commutator subalgebra of G tilde becomes a Heisenberg algebra, which of course has all the fun representation theory of the triangular algebras we spent so much time discussing. In particular, these algebras have an integer grading induced by the Laurent polynomials that affords the curious concept of graded dimension, which allows us to make contact with modular forms. Indeed, to paraphrase Terry Gannon, vertex operator algebras are essentially a way to join Lie algebras and conformal field theory with modular stuff. For this particular example, we find that the graded dimension of the integer-graded Heisenberg algebra amounts to 1 over the Dedekind eta function, exponentiated by the dimension of our original abelian Lie algebra G. When we make contact with conformal field theory, we'll see that this essentially amounts to the partition function of said theory. Let's now preview our new business, that of formal series. To that end, consider the space of maps from an underlying field F to some vector space, V. We will write such things in a peculiar, if suggestive way, as a sum over the would-be monomial term with some coefficient. If that's too awkward, you could try to represent it as an integral, or somehow treat the coefficient as a function of n in F, although we'll typically reserve that last type of notation for vector spaces that service as endomorphisms, or operators of some other space. In the present context, z, or z for you Brits, is a formal variable much like those used in our previous study of Laurent polynomials or graded dimension. It will occasionally serve double duty as a traditional variable when it makes mathematical sense to do so, say in the context of finite polynomials or something of that kind of well-defined sort. But for what it's worth, we can just consider it as a bookkeeping device at this point. Now let's consider V of Z with those curly braces as a set of all such maps from F to V, which we now call formal sums. We note that these formal sums are a vector space, where vector addition is essentially pointwise addition over F, and scalar multiplication is exactly as you'd expect it to be. Some useful subspaces of these formal sums include things we are already familiar with. The vector spaces of polynomials and Laurent polynomials with finitely many terms are great examples. Those here are represented by V with square brackets. Here, the space of formal sums, or potentially infinite sums, essentially indexed by the natural numbers, is represented by 2 square brackets. Of course, we can also include infinite Laurent polynomials in a similar manner. FLM remark that if V is an associative algebra, then so too are the finite polynomials, as well as the Laurent polynomials, as well as the infinite polynomials with positive powers of Z. The space of infinite Laurent polynomials isn't quite an algebra then, and runs into some trouble. To motivate why you might worry about, say, inverses, why you'd be happy with infinite polynomials in positive values, or all negative values as the case may be, you could think about the modules of Heisenberg algebras that we've studied so far. Now, here's a little more potentially confusing bits of notation. For a finite Laurent polynomial V of Z, we might as well allow considerations of, say, V of A, since this is certainly a well-defined thing to do. For the infinite polynomials, this is less clear what that would mean, so we'll allow a scalar multiple of the argument instead. Note that this is distinct from scalar multiplication, as you might find by treating these as vectors in a space of formal sums. Okay, this is all rather detail-oriented and super complex. And there's a reason for that. Basically, all of this stuff, all these formal series, are trying to model quantum fields, which are notoriously unruly objects. For the mathematicians in the audience, I'll do a lightning review of some details of quantum theory here, but I will absolutely make a brief and hopefully complete summary video of the relevant details from quantum mechanics and quantum field theory as soon as I can. In quantum theory, we have physical states and operators upon those states. An operator, such as, say, phi of z, is kind of like a formal sum. It might look like a Fourier series, in fact, but the Fourier coefficients are actually operators on the quantum states. Hopefully, these exponential functions, or plane waves, remind you of the formal variables q or x we studied towards the end of Chapter 1. A quantum field theory is typically equipped with a vacuum state. And if you want to read into this as an analogy with Heisenberg algebras, that is totally appropriate to do so. In physics, we typically attribute the vacuum to be the absence of particles, although the interpretation of that statement could be a series of lectures in and of itself. Essentially, half the Fourier coefficients, those corresponding to positive modes of phi of z, annihilate the vacuum. Hopefully that sounds familiar. Those with negative modes, here alpha star n, essentially act as particle creation operators. But we get the same sort of tower of descended states that we would get in the representation of Heisenberg algebras that we saw in Chapter 1. Now, vacua for interacting quantum field theories get rather messy in general, and it is a serious course of study in its own right. Fortunately, we won't have to worry too much about the details in what follows. Indeed, at this point, we should probably mention that things simplify dramatically, and the symmetries of the system include the so-called conformal transformations, which you can think of as rotations and scale transformations, and well, basically any kind of transformation you can do to a system that preserves angles between intersecting pairs of lines. Another way to think about that is simply scale invariance, although strictly speaking, scale invariance is a subset of conformal invariance. Nevertheless, in conformally invariant quantum field theories, there is no set of characteristic length scales to be found. This fact simplifies the formalism immensely. Indeed, the space of states are essentially reduced to representations of the relevant conformal algebra, which gives rise to a sort of state-operator correspondence that affords the main concept that we'll use to bridge the gap between physics and algebraic methods studied so far, the operator product expansion. If phi sub I and phi sub j are some operators in a quantum field theory, which you can model as some formal series associated to a vector space of endomorphisms for some specific vector space, the main idea here is that their products close into an algebra of operators whose coefficients are singular functions of the relevant formal variables, although really, with poles of some finite order. In ordinary quantum field theory, these operator product expansions would be asymptotic, and exponential terms associated to the various length scales in the problem would arise. But in a conformally invariant quantum field theory, such terms don't exist, and so we can think of the operator product expansion as a legitimate algebraic system, which gives rise to the concept of a vertex operator algebra. Of course, in 2 dimensions, the conformal group is SL2C, which has a local extension to the Virasoro algebra. So hopefully this motivates some of what we've been up to. But, that's the end of our little preview. Next time, we'll investigate the details of formal series much more intensely.